Welcome back, everybody, to episode 58 of the Quantum Science Seminar in the fall 2021 season, which today will be all about gravitational wave interferometry. As usual, we would love to have your questions. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. As always, please note that there's a 30-second time delay between what we're doing here and what you're seeing as live on YouTube. And with that, I'd like to hand over to Andrew, who's going to introduce our speaker today.
Thanks, Sebastian. It's a great pleasure to welcome today's speaker, Sheila Rowan, to the Quantum Science Seminar. Sheila is originally from Dumfries in Scotland and completed her PhD at the University of Glasgow before being a researcher both at Glasgow and then at Stanford for some time. And since 2006, she's held a position as a professor for experimental physics at the University of Glasgow. Sheila is director of the Institute for Gravitational Research at the University of Glasgow, which is an important part of the LIGO collaboration. And she's an expert in systems for gravitational wave detection and extremely sensitive mechanical systems in general. Her work extends across a broad range of technologies, from mechanical stabilization of optics to low-loss materials and to laser systems and all the ingredients that go into making these really fascinating, complex and important experiments. Sheila has won many awards for her work, including the Fred Hoyle Medal and Prize of the Institute of Physics. She's Fellow of the Royal Society of Edinburgh and the Royal Society of London. She's also, in her spare time, chair of the Programme Advisory Committee for the UK's National Quantum Computing Centre. And indeed, from 2016 until June this year, she served as Chief Scientific Advisor to the Scottish Government. So Sheila's going to tell us today a lot about the technologies that go into making gravitational wave detection possible and where things are now and where they're going in the future. And we're really, really looking forward to your talk. So welcome, Sheila, to the Quantum Science Seminar. It's great to have you with us.
Well, thank you very much, Andrew, for the invitation and for the introduction. And you gave a bit of an outline there of what I'm going to cover today. I'm going to talk about, as the headline suggests, gravitational wave observatories. And in this context, think about them as kilometre scale quantum sensors. So it's a particular view of them, and I think challenges a little bit what people have in their minds when they think of the term quantum sensors and what that means. So this is a very different kind of quantum sensor. So I'm going to talk about gravitational waves. I'll tell you a little bit about what gravitational waves physically are to try and give some intuition on that. The instrumental challenges that got us to the first detection of gravitational waves, where we are now, and then, as Andrew mentioned, a bit of a look to the future. So since we're going to talk about gravitational waves, it's helpful to have a little bit of a background in terms of gravitation, what gravitation is, and how we think about it. And of course, for many years, and again, people are still taught, because under many circumstances it works exceedingly well, we had Newton's theory of gravity. And it's familiar to many of us, the idea that if you have two masses some distance apart, they feel an attractive force that depends on their separation and on the masses themselves. And that theory works beautifully in many, many ways, but it does have a very uncomfortable feature, which is that if we have two masses that feel an attraction, depends on the distance between them, and that distance changes, the force between the masses, that gravitational attraction in Newton's theory, changes instantly. And so if one of those masses is here on the surface of the Earth and the other mass is far, far away, somewhere out in the universe, and the distance changes, that would be known about, between the masses instantly, and that's very uncomfortable. It feels wrong, and of course, special relativity actually tells us that no information can be carried faster than the speed of light, and that includes gravitational information. So in other words, there must be, from special relativity, gravitational radiation, traveling gravitational signals. So special relativity tells us that. Actually, general relativity then codifies that. It actually describes in more detail what in this picture gravity sort of does and how it manifests itself. So what general relativity says, if you imagine here, you've got a flat, empty universe with no mass in it, and it is flat, a flat grid, marking out distances. If we add to that universe some mass, we add a star or we add a planet, general relativity tells us that that mass will curve the space-time around it. So you see here this dent that's been caused in a rubber sheet by the presence of mass. If then that mass, or rather, if a second object, a second mass is added to our universe here, you can imagine it will appear to roll down that curve. It will create its own dent, and these two objects will try and roll together. So general relativity you can think of as a geometrical theory in which the tendency of objects to appear to be attracted together is actually caused by the curvature of space-time. That curvature we can think of as representing gravity. And so if these masses move, they change their sort of distribution in space, the curvature changes, and actually across our flexible rubber sheet, changes ripple out. And those changes in the curvature of space-time are what we call gravitational waves. So to give a bit more of a picture of how we can physically envisage this, we think of those field equations of general relativity having wave solutions, that they are produced by a changing configuration of mass. Think of our two objects rolling around on the rubber sheet there. That the induced sort of wave solutions travel, predicted in general relativity, at the speed of light. And the physical effect that they have is to change the effective distance between markers on our rubber sheet there, inertial points in space-time. And this is a transverse wave. So that effect happens transverse to the direction of travel. So what does that look like? There's a bit of a mouth, that's a bit of a mouthful to sort of envisage. So if we look at our animation here, if you imagine that this is a cylinder, marking a cylinder in space, the effect of a gravitational wave sort of traveling in a direction down the center of this cylinder is to distort the shape so that it stretches in one direction and simultaneously compresses in the other, and it does this in an oscillatory fashion. So it's quite hypnotic to watch. If we take a slice through that cylinder, so you can think about a slice through the screen here, and look at what's happening to the distortion. If we take a fixed position in space while gravitational waves pass through it, you can see here our original ring of dots is distorted into an ellipse in one direction, squashed in, stretched, and it does that in an alternating fashion. So that's the physical effect, is the stretching and squashing of distances in this very characteristic fashion. Now, if we want to sense that effect, if we want to build a sensor to detect the passage of gravitational waves, then that's the physical effect we're looking at. And in terms of instrumentation, there is an instrument that naturally lends itself to measuring the differential motion of points that you can imagine, say at the top of our oscillating circle there, and at right angles on the side, and that's a Michelson-type interferometer. So again, many of you will be familiar with this. Light from a laser comes in, hits a beam splitter, is split into two, travels out along the two arms, is reflected from mirrors, recombines at the beam splitter to form an interference pattern. And so the passage of a gravitational wave through such an instrument would stretch one arm of the Michelson while simultaneously compressing the other. And then that happens in an oscillatory fashion. So if we have a photodetector, and we literally look at the outputs there at the beam splitter, we would see a change in the interference pattern. We would see light and dark, sort of changes in the light and dark fringes there as a gravitational wave passes through. So that's the principle, but the challenge comes in the practice, which is how big are the signals that we're trying to measure. So let's imagine our interferometer has some arm length L, and the effect of a gravitational wave is to stretch or compress the arms by some amount delta L. So we can work out the size of the gravitational wave amplitude that we call h, and we define that to be 2 delta L over L, twice that small change over the original arm length. And for the sorts of large masses that we have far out in the universe, we can calculate from general relativity the size of a typical gravitational wave, the strength of the effect, which is about sort of less than or equal to about 10 to the minus 22. And we calculate that from astrophysical masses and general relativity. Delta L, then we can rearrange that equation to give us the fact that delta L, the induced effect, is h upon 2L. So if we decide we're going to build a Michelson on a tabletop, one arm interferometer, with an arm length of about 1 meter, we put that into our equation. L's 1, h is 10 to the minus 22. So that tells us that the delta L, the amount that one of those mirrors would effectively move, is about 10 to the minus 22 meters, which is a tiny, tiny amount, very, very small. And fundamentally, that's why we don't build tabletop devices. We look and we want to maximize delta L, so we make L, the arm length of our instruments, long to maximize the signal we're trying to detect. And that leads us to the idea of kilometer scale devices to get the signal to a size that is manageable to detect. Now, what sorts of sources of gravitational waves are we talking about? Well, we want large masses, dense objects. And so, of course, the most extreme we can think of in terms of those characteristics are black holes. The end points of stars that have run out of fuel, they no longer are producing energy to hold them up against gravity. So they collapse, blow off their outside core, with the core of the star collapsing down to a region of space where gravity is so strong that nothing can escape its pull, not even light, hence black holes. So in our animation here, we see 2 black holes that have been caught in one another's gravity, have been spiraling round, getting closer and closer together as they radiate away energy out in the form of gravitational waves and eventually merge to form a new black hole. So I'm going to run that animation one more time, because you imagine there's our 2 black holes somewhere far, far away in the universe. The colours here are sort of illustrating the dents in space-time that we talked about earlier. Underneath, at the bottom of this animation, you'll see being sort of filled in slowly an oscillating wave. And what that represents is the signal that we would detect with our detector here on the surface of the Earth from the movements, the oscillatory movements of the mirrors in our instrument. And they oscillate faster and faster as the black holes are getting closer and closer. The signal gets larger as the black holes get closer and closer together, until eventually it reaches a peak as the black holes merge, form a new black hole, which then oscillates a little bit and rings down as it's born. And so the signature of that event has been generated by the black holes spiraling in to collide. The gravitational waves produced then spread out, ripple out across the universe until they reach us eventually here on the surface of the Earth. And that's a very characteristic signal. And that is just the kind of signal that was first detected back in 2015, reported in 2016, as picked up by the LIGO observatories, one in Hanford in Washington State in the US, the other in Livingston, Louisiana. And you can see this is a cutout from that first publication. And you can see those oscillations getting faster and faster, larger and larger as the black holes collided. Now, buried in that signal is the information about what generated it. So by picking up these sort of wobbles of oscillations of inertial points in space, we do astronomy and astrophysics. We can tell from the shape of that signal that we had two black holes, and they were black holes, that they collided about 1.3 billion light years away from us, that the final black hole was about the size of Iceland, but about 62 times the mass of our sun, and that it was spinning about 100 times a second at nearly half the speed of light. And all of that is buried in that signal. So that's our end point, what we're trying to do. And to remind you, the sensing challenge is that the peak-to-peak motion there is equivalent to about 4 times 10 to the minus 18 meters. So these are very small signals. So I've been drawing stick diagrams of Michelson interferometers, but as you might guess, to actually be able to measure with that precision, these are mirror displacements, remember, less than about 1,000th of the size of a proton. Reality goes in a much more complicated direction. So I'll give you a quick tour of some of the developments and of the instrumentation that got us to that point. Here's a picture of the outside of the observatories. You can see Hanford detector top left, Livingston bottom right, with that characteristic L shape. These are managed by Caltech and MIT, but actually are relevant and contributed to by the LIGO scientific collaboration, more than 1,000 scientists around the world. Working from the outside in, there's those two long arms, 4 kilometers long in the case of LIGO. We don't want any gas molecules interfering with our laser beams, so there are vacuum tubes that run the 4 kilometers, about 1.2 meters in diameter. Over the top of those, there's a concrete cover to protect them. You can see from the picture on the top right, that's from the Hanford site, that external cover is indeed relevant. The civil engineering challenges are not insignificant. That tube has to be straight, again, not following the Earth's curvature, which eventually starts to be an issue. Inside those tubes are, of course, a complicated optical system. You can see driven by a laser to produce a laser light, and this is Michelson-type, but you can see the addition of many more optical components. The laser light is filtered through an input cavity, again, to clean up its beam. It then goes through a mirror, again, which is partially transmitting, hits the beam splitter, is sent out along the two arms, are 4 kilometers long. You can see each arm now has in it actually another cavity to build up the light in that cavity, enhance the sensitivity of the instrument. Inside each cavity in the arm, there's about 800 kilowatts of CW light, continuous wave light at 1064 nanometers. So this is a high power system. And you'll see pictures there, and I'll talk in a little bit more detail about these, because what we have to do, as you might imagine, is isolate the mirrors in the interferometer from external disturbances. Because there are many things, as you might imagine, that can disturb and cause motion or apparent motion of the mirrors at a level that would be much higher than a gravitational wave signal. So perhaps the first and most obvious of those is seismic noise. Now, to help interpret the plot that's on the screen here, along the bottom, you'll see frequency going from 10 hertz up to a few kilohertz. So this is the spectrum. In this case, the spectrum of expected noise in the instrument. Up the left-hand side, you'll see strain. Remember, we calibrated our gravitational wave size in delta L over L. So this is telling us about the size of the relative noise sources as a function of frequency in the instrument. Now, seismic noise is mostly a problem at low frequencies. You can see those big blue arrows pointing to where seismic noise is an issue. And it contributes in a couple of ways, where we're searching for gravitational waves, sort of in that mid-frequency band there. Seismic noise can try and shake the mirrors, but actually at even lower frequencies, we do not want the mirrors to shake. We're not looking for gravitational waves there, but we need to be able to point the mirrors in our interferometer. So we need to be able to control them. So we don't want the seismic noise to interfere with that. To reduce the seismic noise, we do it in a couple of ways. There are active platforms that are servo-controlled to control their position and sort of reduce seismic noise. And at even a lower frequency, right down at the 10 hertz and below band, there's straight Newtonian noise. So local objects, local masses, people walking past our test masses can exert a straight gravitational pull on them, and that we can't shield against. So the seismic isolation system comes in different stages. We both have active seismic platforms, either from which our optics are suspended or on top of which the optics sit. I won't go through in detail, but these give about 10 orders of magnitude suppression of ground motion above 10 hertz. And there's a whole bunch of sensors whose signals sense motion. Those are combined in various control loops to then control the surface of these seismic isolation systems to reduce the external ground vibration getting and prevent it or reduce its effects on the test masses. At high frequency, we start to hit forms of quantum noise, and at high frequency we hit shot noise. So the sort of statistical fluctuations in the light hitting the photodetector actually start to be a limiting noise source in the instrument. We can reduce the effects of that by increasing the laser power and the light in the system. If we do that, though, we actually start to increase another source of noise at low frequencies, which is radiation pressure, which is the other side of our quantum noise problem, is that every photon that bounces off one of our mirrors transfers momentum to it. So if we turn up the laser power, we reduce the effects of shot noise, or the sensitivity limit due to shot noise, but we have to be very careful that we don't also increase to unacceptable levels the radiation pressure that's actually causing the test masses to move. There is in fact a balance of those two that can happen, which is the same limit to sensitivity at that frequency as you get from applying the Heisenberg uncertainty principle to measuring the position of the test mass. It's the standard quantum limit. And Advanced LIGO is designed such that it should effectively reach that with a 200-watt laser and 40 kilogram test masses. So that 200-watt laser is a neodymium-YAG laser, highly stabilized in power and frequency. And there's a whole set of external loops and ways in which we use the detector itself to provide that stabilization. And that was designed and contributed by the Albert Einstein Institute in Germany. And I won't go into detail there, but there's some nice papers that describe that particular system. In the mid-frequency band, we're fighting a different noise source again, which is Brownian thermal noise. Our mirrors have atoms, they're made of atoms and molecules. They're just at room temperature. So each of those individual atoms and molecules in the mirror is vibrating slightly, and it's coupled to the molecules around it. So overall, that results in motion of the mirror surface. That's also true for the fibers that we use, because on top of our seismic platforms or suspended from them, we have another 4 stages of isolation, of seismic isolation, this time in the form of pendulums. Because if you take, it's a simple way to isolate from seismic noise, is to take the object that you wish to isolate, suspend it as a pendulum, and above the resonant frequency of the pendulum, that provides seismic isolation to the suspended object. You can increase that by stacking up your pendula. So here we have a 4-stage pendulum, the bottom one of which is it's our mirror at the ends of our interferometer arms, which represents our marker in inertial space. That is the thing whose position we are sensing to try and sense the motion, the effects of gravitational waves causing the mirror to move. Those mirrors themselves have to be chosen from the low mechanical loss material to give us good thermal noise performance. Fused silica turns out to be very good. We maximize the goodness of that fused silica by actually suspending the 40 kilogram fused silica test mass on 4 fused silica fibers, which also have low thermal noise. And that was a contribution to LIGO from the UK, again led by my group in Glasgow, but with colleagues across various institutes in the UK and at Rutherford lab. Working down, so we've gone through the seismic isolation, the 4-stage pendulum, we get to the mirror at the bottom, and those are crucial elements in the detector. They are macroscopic, as you can tell, 40 kilograms, about 34 centimeters across, about 20 centimeters thick. And we want those mirrors to be essentially motionless as we can make them, because those are our inertial markers in space-time. But they also have to practically serve the function of being the mirrors in our cavities. So there are tight optical requirements on those. The input test masses at the sort of positions near to the beam splitter, again, are very high quality suprasil, has sub half ppm per centimeter absorption at 1064. Remember, these are supporting a substantial amount of CW laser light, so they have to be very low absorption. The end test masses are also suprasil, slightly different quality because it's their very high reflectors. The optical coatings are extremely important because they also have to be very low absorption, low optical absorption, but they also have to have low mechanical loss to give us low Brownian thermal noise again, because they are the points in the instrument that the sensing light touches. And so the few micron thick optical coatings that go in the front of these mirrors can in fact have thermal noise that limits the sensitivity of the entire 4-kilometer instrument. So we have to design those very carefully, and both in my group in Glasgow and actually at Strathclyde, there's a lot of work that goes into that. So these, and they also have to be very homogeneous, again, across the size. So these are ion beam sputtered to get the properties that we need. These ones were produced by LMA in Lyon. It's one of the few labs in the world that can produce coatings of this quality. Even at those ultra low absorption levels, there is still some absorption of the laser light. Remember, you can have hundreds of kilowatts in there. These are 4-kilometer long cavities, so they have a very shallow radius of curvature to have a stable cavity to support the resonant laser light. So even with the low absorption that we have, it requires active thermal compensation to compensate for the thermal distortions induced in the mirrors. That happens in a couple of ways. There's at various points in the instrument radiative ring heaters. You can think of them as big toasters and big heating elements that are used to take out some of the lower order thermal distortions. And for higher order distortions, there's a carbon dioxide laser beam projection that takes out some of the higher order distortions to make sure that, again, as our interferometer can remain actually with all its cavities locked and operating as an instrument. So I've given you a sort of whistle-stop tour of from the outside in to the inertial points, the inertial markers that we have in the operation of these gravitational wave detectors. So I will pause there and see if anyone has any questions at this point.
Thanks, Sheila. Can you hear me?
I can.
Okay, so we already have a couple of questions from the audience. The first one is about some technical question about how does the vacuum need to be?
So that's a good question, and off the top of my head, I don't remember the exact number, but it is an ultra-high vacuum system. I can check, but I don't have the number to hand. But it's a major sort of effort to get the good vacuum that we need. And it comes in, it's important in a remarkable variety of ways. In the ways that I talked about, that we do not want refractive index fluctuations being caused by the beam traveling, through gas. But if you take a look at the picture that's currently on the screen with our test mass, behind that test mass, there's actually another mass suspended with a little gap in between. And in some of the optics, there's electrostatic control applied from the suspended mass to the test mass. So it's a certain distance away. And if there are residual molecules of gas in that gap, you can get squeezed film damping, which actually is an additional unexpected source of noise. Again, there was a lot of work done both by LIGO and actually by colleagues who work on the space-based detector LISA to understand, because it only becomes apparent once you get to these very small displacement, small precision measurements that it starts to show up. So it does have to be a very good vacuum for a whole variety of different reasons. Apologies, I don't remember the exact number offhand.
Thank you. So again, about the technology, can you comment on the choice of the laser wavelength maybe? And we're curious about whether it would help to have two different wavelengths running an interferometer.
So that's an interesting question. So the choice of the wavelength. So originally, the first work that was done, or original work was done, a lot of work was done looking at using argon wavelengths. So some of the prototypes were actually run with argon-ion lasers, and in the green. And there was a lot of attachment to the green wavelength. It turns out the sensitivity that you can get is a function of wavelength, and actually the shorter the wavelength, the better. Again, when you work out the sensitivity of the instrument, short wavelengths help. However, you also need high powers. And again, if folks sort of think back to the days of argon-ion lasers, I mean, we're talking about a 200-watt laser here. And so 200 watts of green light, certainly in the development stages, was not easy to get. You can find papers with people, actually there's a paper from Glasgow, I think, that talks about coherent addition of the light from argon-ion lasers to try and get up the powers. Part of my PhD thesis actually was on frequency doubling of 1064 light to get to 532, and people considered that. But it was technologically easier just to go straight for 1064 with solid state laser development. There are other sort of optical issues that come in with the shorter wavelengths with the green, how the green interacts with materials, again, that are not so bad if you're at 1064. But it's partly engineering and a bunch of different materials trade-offs and laser engineering trade-offs that eventually resulted in the choice of 1064. I mean, it has to be a wavelength that's compatible with the materials choice, again, so it works well with fused silica. But for a while there was a whole train of research, and I'll talk later about where we might be going next. That might not be 1064, that might be 1550 or 2 microns.
Thank you. We have two questions from the YouTube channel. One is from Gadi Afek. Why do you need 4 stages of hanging the mirrors? Would you gain by making it 10 stages or 100 stages?
So the answer is yes, you would. And indeed, I've talked about LIGO in the interest of time, and it's the one I probably know best. However, Virgo, which is I'll talk about shortly, the French-Italian instrument, has at least 6 or 7 state pendulum stages. So they have what's called a super attenuator with many more stages of isolation, and they have many fewer stages of active isolation, and there are pros and cons to both approaches. So LIGO has, or Advanced LIGO has several stages of active, several stages of passive. Virgo has many more stages of passive and fewer stages of active, and so there is a trade-off, but yes, you do gain by stacking up the pendulum.
Okay, then maybe one last question for the moment. Maciej Malinowski wonder if your system deteriorates over time and whether you need to replace some parts regularly.
Thanks, really good question. And I will talk a bit, in some cases actually, as we've operated the instrument, its sensitivity has improved over time, as people understand what the limiting noise sources are and how to tweak the operation of the instrument and the control systems or such to improve its sensitivity. However, we do typically have an observing run and then stop and then improve the instrument. And that sometimes does involve replacing parts. And again, I'm preempting the rest of my talk, so I'll stop there and say, keep watching and I'll talk more about this.
Okay, thanks a lot, Sheila. So if you want, you can maybe move on and we will ask the rest of the questions at the end.
Certainly. Thanks very much. So that was a whistle-stop tour of the technology of one instrument, of the Advanced LIGO, in fact, instrument. But in fact, there are a network of interferometers either running or planned around the globe. You'll see there the Hanford and Livingston instruments that I talked about with their 4-kilometer long arms. I mentioned the Virgo instrument, which is located in Europe. It's located in Italy, but again, it's a collaboration of several European countries. In Glasgow, we're members of the LIGO collaboration and also the GEO collaboration, which is a shorter instrument, 600 meters in Germany, and which actually tested quite a few of the technologies that have now been implemented in LIGO. Again, our German colleagues supplied the laser, we supplied the design for the suspensions, and all of that was tested in GEO. There's also a detector in Kagra, which is in Japan, called Kagra, which is a very interesting instrument, which is cryogenic, which is underground. It's 3-kilometer long arms. And in the future, there will be a third LIGO-like instrument located in India. And these form a number of collaborations, which historically have been separate, but in fact work very closely together, particularly both on actually sharing instrument knowledge and also particularly on sharing data and analysing the signals from these instruments. So we do work very closely together. Now, why do you need, you might ask, all of those instruments? Well, it's to do the science. We're picking up signals that are originating somewhere out in the universe. And each detector on its own has some directional sensitivity, but it's not fantastic. You can think of them as more like microphones than telescopes. They have some amount of all-sky sensitivity. So how do we know where in the universe our signal is coming from? And there are good reasons for wanting to do that, so that if whatever's out there is producing light or electromagnetic waves as well as gravitational signals, we can give that information to our colleagues with telescopes who can then look at that portion of the sky, but they need to know where to look. So with one instrument, you don't do terribly well. With 2 observatories, they're the LIGO instruments, you get some directional information, and you get it from the timing of when a signal arrives at one instrument and subsequently at another instrument. It takes time because, remember, general relativity predicts that these signals travel at the speed of light. So if, say, a signal arrived at the Livingston Observatory first and later in Hanford, you'd know that was coming from the southern hemisphere. 2 gets you some information. 3 instruments, 3 observatories, you do better. And the plot there is sort of the sky unwrapped onto the slide. The blue circles are the sort of 90% confidence limits of how well, with 3 observatories, you could tell the position of a source on the sky, and the X's are, even with 3 instruments, there are still some places you would have no sensitivity to. With 5 sites, so Hanford, Livingston, LIGO India, detector in Japan, and Virgo in Europe, that uncertainty shrinks, and so you do much, much better in terms of telling where in the sky something has come from. So we need that network. There's good underlying science. So how well are we doing now? Where have we kind of got to? Well, you'll recognise this plot. There's frequency along the bottom. This time it's not strain but displacement. You can think of the shaking of the mirrors up the side. For what's called the second observing run of the LIGO instruments, the two observatories, the sensitivity of one's in red and the other in blue, and then the curve at the bottom there is the design sensitivity. So that's where we were sort of back in 2017, again, when we did a second observing run. You'll notice not yet at detector sensitivity. So the first detections, indeed, even before this in 2015, were made with the instruments not at design sensitivity. Improved over initial stages, but not at design. With, however, that sensitivity, we have now managed to measure quite a few gravitational wave signals. The picture that you see here, again, is illustrative of the size of black holes that we've been detecting. So let me help interpret. Up the left-hand side is the mass of the black holes in number of times the mass of the sun. So 5 would be 5 times the mass of the sun, 20 times the mass of the sun. At the top, the heaviest sort of circles there are the pairs of black holes that have been detected colliding by the LIGO Virgo network. So up to 80 solar masses in 2017. The sort of purple individual circles there are black holes and their masses that we believe exist from electromagnetic observations of the area around the black holes. Down at the bottom, the yellow dots are individual neutron stars, the stage of stellar collapse before you get to a black hole. Again, the yellow ones are ones that we have observed from electromagnetic signals. And in the middle there, you'll see something this time picked up by the LIGO Virgo network, but not a black hole collision. This time, 2 neutron stars that spiraled into collide. So many black holes detected colliding. But this, again, I can't resist, although I'm talking mostly about technology today, to give you a little bit of astrophysics. It's quite a remarkable event. 17th of August 2017, picked up a signal, saw the wobbling signal, and from its shape could tell that it was not black holes colliding, it was something different. It was these neutron stars colliding. Now it turns out from the black holes colliding, we get the gravitational signal, but if we look at the sky, we look at the universe where those gravitational signals have come from, we see no electromagnetic signals, it's just dark. So we're seeing them only through we're picking them up only through their gravitational signals. But neutron stars are made of matter, and when they smash into one another, they produce electromagnetic light across the spectrum. And when this event was detected in gravitational waves, there were many telescopes that also were able to observe that portion of the sky, and that one detection produced a vast amount of physics, confirmed that neutron star collisions people believed, but this was confirmation that they are the source of gamma ray bursts, these mysterious bursts of gamma rays. Allowed us to confirm the speed of gravitational waves compared with the speed of light, again, which are identical, again, to a small precision, a small difference there, which is interesting physics associated with that. Many other things, including an independent measure of the expansion rate of the universe through gravitational wave detections, and confirming that gold and platinum being produced in the universe, which is what you can see in this lovely artist's impression, are coming from the collision of neutron stars. A remarkable set of physics. So from that event. Now, it was a very good question. Do we have to do things to the instruments? Well, we've carried out now a third observing run. Those were results from the second observing run. And in between, we turned the instruments off and spent quite a bit of time making instrumental changes and commissioning. I said at high frequencies, one of the limits was shot noise, and you can improve that by turning up your laser power. Indeed, the original runs were not carried out at full laser power, so the laser power was increased between observing run 2 and observing run 3. To further improve shot noise, there was also the injection of squeezed light into the interferometer. So to improve so we said both shot noise and radiation pressure are manifestations of quantum effects, and by squeezing the vacuum, so this is vacuum fluctuations that can enter into the unused port at the beam splitter. By preparing those, we can sort of reduce either the phase uncertainty or the amplitude uncertainty associated with the light. And in doing so, by doing that, we can inject those prepared states, which add to the light in there, and in this case, reduce the shot noise in the instrument. So that, again, was one of the techniques that was implemented before '03, and both of those target the high frequency sensitivity. However, remember, we've turned the laser power up, so that does increase the radiation pressure, that buffeting of the suspended or carefully suspended test masses. We turned it up, so there are technical challenges, including increased absorption potentially at the test masses. We tackled those again by installing little dampers onto the test masses. As the mechanical motion of the masses interacts with the light field, we can get instabilities, and so these acoustic mode dampers sort of damp some of the mechanical resonances, and again some additions to the control system to compensate for, again, radiation pressure induced torque on the test masses. Again, there was this question asked about replacement. Actually, between those runs, the two end test masses were replaced at both sites in the instruments with essentially mirrors that had lower scatter and higher reflectivity coatings, which helped the lock acquisition. Again, we have control systems that control and lock the position of the mirrors. I mentioned electrostatic drives. We can have an issue that these test masses, which are of course insulators, can charge up, and that can come from, and again we talked about the fact we need good vacuum. There are ion pumps on the system, ionization from UV light that comes out of the ion pumps produce, again, if you ever see them, there's a sort of glow. With metal in the system, we can end up with charge then being deposited, the UV light causing charge to be deposited on the test masses, which then builds up, can interact with the structures around it, and then we start to have problems controlling the mirrors. So those pumps were relocated and the UV light baffled. A whole bunch of other things. I won't go through them all, but there's a whole set, and so we stop, we turn off, and we improve. And there are good reasons for doing that. Again, sometimes our astronomer colleagues say, you're seeing things, don't turn off, don't do that, just keep measuring. But this plot shows why we do turn off. Those improvements that I talked about between the second and third observing runs, '02 and '03 there. This plot shows along the bottom just time, number of days of running. Up the side, the cumulative number of events or candidate event sort of gravitational wave detections that we had. And you can see the rate between '01 and '02. You know, as we ran the instruments, we made a series of detections. We stopped for a while, again, a reasonable amount of time, made some improvements, but when we turned back on, you can see the rate of detection significantly increased. So there are good reasons why we turn off and improve the sensitivity of the detectors. So we now have many more events detected, tens of detections again published since the start of the third data run, still analysing some of that data. I won't go through this again in detail, but you can do different science once you have a number of events. You can do statistical things that you simply couldn't do before. So again, we're exciting science. We will, again, we're planning for the next observing run, but as with much of the world, again, this is on the LIGO website, so you can look up and see the latest status. COVID, of course, has interrupted everything. It's impacted things in many ways, this included. And so not before August 22, again, is the current schedule for the next observing run. But again, it's due for an imminent update on news, so you can watch that space. So that's kind of where we are. What's coming next? Well, you can see all the technology developments, and so we have been thinking hard, because it makes such a big difference to the science, about how we can improve the detectors further. You'll be getting used to seeing these plots, frequency along the bottom, this time it's strain again up the side. And those coloured curves tell you about the different sources of noise that are limiting the design sensitivity at different frequencies. So targets, well, there's Newtonian noise at low frequencies, and actually you can't shield against it, but there may be ways that you can mitigate it. Squeezed light, again, we already have some squeezed light on, but there's more that can be done. Coating thermal noise, I talked about, again, it's a materials question. Those few micron thick optical coatings, what can we do? And suspension upgrades, can we improve further the isolation and thermal noise from the suspensions? And we believe we can improve the sensitivity a bit further with kind of moderate upgrades, and this work is well underway. A staged implementation, some aspects of which will be in place for the next observing run. And this, I've talked about LIGO, but there's a very similar upgrade planned again for our partner instrument in Advanced LIGO. So I'll talk just about one of those, which is, we talked about squeezing, and if you remember, again, we talked about this earlier. We have shot noise, which is resulting from the fluctuations in the arrival time of photons detected at that interferometer output, and radiation pressure caused by the photon flux banging off the interferometer mirrors, and their common origin are the vacuum states entering the output port of the interferometer. So the squeezing that I talked about, which actually was first implemented in GEO and now in LIGO and Virgo, has sort of, it redistributes the quantum uncertainty. This is the way it's been used to date to reduce the shot noise, but again, the uncertainty principle means you get a kick up in the radiation pressure. There are, however, ways that you can get around that to simultaneously reduce the shot noise at high frequencies and the radiation at low frequencies by some more manipulation of the light that you inject, or the squeezed vacuum. And there's a filter cavity that's used to do that. That means when you manipulate the quantum uncertainty as it's injected, you do that in such a way that it correctly, at the higher frequencies, reduces shot noise, but then at lower frequencies also can reduce the radiation pressure. So that again will be, again, I won't talk about it in detail, but I've put the reference on the slide there that describes some of the techniques and plans associated with that. So that can be done in the current infrastructures, but eventually we will hit limits. These are 4 kilometre long. Remember, we said signal gets bigger as arm length gets bigger. These are 4 kilometres, so that will happen. Some of these instruments actually have been running already for a remarkably long time. And so there are things we can do, but things that will be too hard to put in these infrastructures. If we want to go cryogenic, I said the mirrors are at room temperature and thermal noise is an issue. Say we want to cool things down, installing cryogenic apparatus, there'll be limits to what can be done there. We can average away the thermal noise by increasing the size of the beam that hits the test masses, but there are limits again with the size of the tubes as to what you can do. So we may, and think we will, eventually need to go to new infrastructures. Longer arms, 10 kilometres, 40 kilometres. Newtonian noise, it turns out one of the main drivers of that is actually ground motion, not straight seismic motion rattling the mirrors, but the gravitational pull of the motion of the Earth pulling on the masses. Turns out that goes down if you put the detectors underground, so we could move to an underground site. Turn the laser power up even further. If we do that, we've got to think about radiation pressure, so we'll want heavier optics, 100 kilograms, 200 kilograms. If we want to go cryogenic, fused silica is not the way to go, because actually it has material properties that mean its performance gets worse at low temperatures. We need something we can get in big pieces, good quality, so silicon or sapphire, silicon well developed for the semiconductor industry, grow large bulls. Sapphire, again, there are companies who make large pieces for windows on sort of military things. If we do that, we will have to switch wavelength if we go to silicon, 1550 or 2 microns, and there are trade-offs there, and a lot of research ongoing to understand how silicon behaves when illuminated with light at those different wavelengths. Lower thermal noise coatings they still turn out to be one of our limiting sources. Ion beam sputtering might still be the way ahead, possibly with different materials, or we can go to crystalline coatings, which have been shown to have good optical performance, but there are challenges with getting those onto the front of these kinds of test masses because of how they're fabricated. We can average away the thermal noise better if we don't use Gaussian laser beams, but we use some more complicated shapes. So a whole bunch of technologies that are under study. And the visions for where these might be implemented, well, in Europe, again, there's been a lot of work in terms of a design study and a recent update to that for a large detector to go underground, envisaged as the Einstein telescope. That's just been this year formally added to the S3 roadmap as a vision for the future infrastructure. Couple of sites in Europe being looked at, again, where that might go underground, one in Italy and one mainland Europe. And in the US, there's an effort to consider a 40-kilometre arm length detector, this time above ground. And there's been a design study just completed, funded by the NSF, to look at what the design for that kind of instrument looked like. Timescales for each of these, again, we're looking at the sort of mid-2030s, again, as we move through the design and the vision for these. So just to finish, pretty much everything I've said relates to the far right-hand side of this plot. I've talked about these Michelson-type interferometers on the ground, studying things like stellar mass colliding black holes. We're searching for signals from spinning neutron stars, potentially supernovae, signals that fall kind of into the audio band. But there's a whole bunch of different sources out there in the universe producing gravitational waves, we believe, over a wide range of wavelengths. And we will need different sorts of detectors to pick up those. So this is really just the beginning of the era of gravitational wave astronomy. We will need new instruments. There's a whole bunch of exciting R&D on enabling technologies still to be done, and I'm sure more discoveries to come along with it. And I will stop there.
Thanks a lot, Sheila. It was indeed very exciting talk, and very exciting the gravitational astronomy. So I would like to ask you a few more questions, other two technical questions. One is about the coatings of your mirrors. There are new crystalline coatings that mitigate Brownian mirror noise. And are there plans to integrate these into gravitational wave detectors?
So there's a lot of work being done on that. So those crystalline coatings at the moment are on relatively small optics, and they are fabricated by growing them on gallium arsenide material. Then they actually have to be removed from the gallium arsenide material and attached to the optic that you want to use. And so on small optics, that is a challenge on its own, but it can be done. And there have been some very nice results, again, from colleagues at Gilla and elsewhere, on showing that the performance, thermal noise limited performance of those coatings can indeed be better than the current ion beam sputtered coatings. But remember, we're instead of a sort of centimetre sized optic, even Advanced LIGO is 34 centimetres diameter, and the future detectors would be even larger. So to take those crystalline coatings, remove the well, first of all, you need to be able to get gallium arsenide substrates that are large enough to grow your coatings on, and that in itself is a non-trivial challenge. At this point, there's a limit to the size of gallium arsenide substrate you can get. You then need to take that coating off, transfer it onto our substrates with absolutely no defects in the interface layer, which of course is quite different than ion beam sputtered coatings, where you take your cleaned optic and you grow the coating and deposit the coating straight onto the optical surface. So it's not without its challenge, but people are definitely looking at that. We actually have been looking at a different, so that's gas coatings, gas coatings We, with colleagues at Stanford, Jim Harris's group there, actually been developing gap coatings, which is lattice matched to silicon. So you can grow the crystalline coatings straight onto your silicon substrate, which removes the step of having to take it off one material and put it onto another, but it requires materials development to do that. So there's a lot of, and again, colleagues at Strathclyde, we're working with Stuart Reid at Strathclyde, who's working in this area. So they're very, very interesting. Again, it's one of the interesting routes for the future, but they're all challenging, so lots of R&D to be done.
Thank you. Another question from our YouTube viewers. Are there smaller events than two neutron stars colliding that you expect to see with their gravitational wave sign in the near term?
So I'm not quite sure, do you mean if that means picking up
the signal,
smaller signals or smaller yes. mass events? So smaller signals. So as we make our detectors more sensitive, we both are able to detect more local events with higher signal to noise ratio. And also we start to be sensitive to events that are further away and thus have smaller signals. And we also can be, by improving the sensitivity, we have a better likelihood of picking up rare events, things that don't happen very often, like supernovae. And supernovae is the sort of classic example of that, where they do not happen all that often, depending on the volume that you look at. As you look at a bigger volume, you've got a bigger chance of catching one. The size of the signal from supernovae is quite uncertain. If a star collapsed in a manner that was perfectly symmetric, it would not produce any gravitational waves. We need what's called a quadruple distortion. It's very difficult to predict the symmetry or asymmetry of a supernova collapse. So there's one, how often does it happen? Two, what is the asymmetry of the collapse? So as we make our detectors more sensitive, we have a larger chance of picking up some of those signals that might be weak. The detectors I talked about in the third generation, the Einstein telescope and Cosmic Explorer, would be roughly 10 times more sensitive than the advanced detectors, which doesn't sound all that much, but you cube that to understand the volume of the universe that you're probing. And for some sources, like the colliding black holes, those instruments are predicted to be sensitive enough, essentially, to pick up every colliding black hole that there is out to the edge of the observable universe. So there's quite remarkable things coming.
Thanks a lot. Maybe one last question, and this is about comparing also the sensitivity that can be achieved with atomic clocks. So the Michelson interferometer senses a length change delta L over L. If I want to think instead of a gravitational wave as distorting the gravitational potential U, what do you think about the perspectives of using atomic clocks to measure gravitational waves? Would one get different kinds of information maybe, or is a Michelson interferometer always better? So
I think you've got to distinguish local gravitational effects from gravitational waves. So there's the local gravitational changes. There are many things that can be very sensitive to local gravitational changes, including, sort of atom interferometers. Atomic clocks, I think it's trickier. There's nothing you can do on a tabletop with an atomic clock, I think. I shouldn't say nothing, but a tabletop localized system, I think, will not pick up the gravitational wave signals. Now, there are schemes that people have considered with distributed clocks
I think we don't have much time left, so if you agree, we will send to you the rest of the questions via email for her wonderful talk.
Yeah, thank you, Sheila, also from my side. And I will wrap it up here and let you know that we are making some changes to the format over the next few months. And as a first step, we're going to go to a monthly schedule with a new seminar every first Thursday in the month. This is the first one of those. This means that we're going to have our next seminar on November 4th. We will, of course, keep you informed by our email list. And of course, you can always find the latest information on our website. If you want to get notified about what we do, please do go to that website on quantumscienceseminar.com. You can subscribe to our email list there and our Google Calendar, and you can follow us on Twitter. You should also certainly check out our sister seminar, the virtual AMO seminar, which is now part of DAMOP, where tomorrow they'll have Stephanie Simmons, who will speak about silicon vacancy centers. And with that, I'd like to thank you for your interest and hope to see you again next time on November 4th. Same time, same place. Bye.